So today we are in the 7th lecture, right? Yeah, keep your mic on. Okay, so let's start. So now, so far we have seen how to realize the DC-DC power converter, and now we have moved towards the control of the same. Okay, when we have realized the power converter, definitely we need a method to control it, and particularly when we are putting it for a drives application, we need to have a good model of the complete system, and then we need to appropriately place the controllers whichever we want so that the drive can perform well under the given situations. So we have modeled the motor, we have modeled the converter, and this is what the open loop system we have got. Now we have seen the advantages or disadvantages of the open loop system. So why we need closed loop system, that we have seen, and then we have gone towards the closed loop control, which is also called as unity feedback system. So we have seen the advantages. What are the advantages? So we can overcome the parameter variation if there is any. We can cancel the noise if there is any. So overall, this performs much better than the open loop system. Now the question comes how to design, because we have two very significantly different time constants, electrical and mechanical, and we are dealing with both of this in the motor drive system. So we need to have different controllers for different subsystems, and something what is called as cascaded control mode, where we will keep one control loop inside the other control loop. So obviously the faster control loop, which is current control loop, will sit inside the slower control loop or the outer control loop. So the outer control loop would be the speed control. It can also be, say, for example, position control or torque control, anything could be there. So we can control everything, any of this, using the current control. That means whenever we give the desired torque or whatever is required torque to maintain this given input, the system can perform according to that. So ultimately here it's not necessary to have only speed. We can have any other quantity, mechanical quantity, of course. Now we are trying to have these kind of controllers, say P, PI or PID. So definitely we are looking for linear controllers, which is applicable for linear system. And these are some of the tools which we will use to design this. So today we will hopefully complete this part. So this week we have got so many things to understand, to learn. So we will see how far we are able to go today. So this is some understanding about linear system. If it is fulfilling these conditions, then we say that the system is linear. And then if we have linear system, one of the tools which is used to design this kind of control structure is Bode plot. So here we have magnitude and phase plot. So in general, if we have a transfer function given like this, which has a constant value, constant gain, and then there is some zero and pole located in the system. So we can draw by first getting the magnitude of that system and then the phase of the system. So magnitude we have seen, we can segregate each and every part, and this part which contains this variable omega can be approximated to either 0 or this linear slope line. So this can be given for these conditions. And what we say that these two curves meet at omega z or whatever corner frequency we are having. That's the nature of asymptotic plot. So we have this curve which is predominantly in this zone, and then we have this curve which is predominantly in this zone, and these two curves match basically at this point, which is the corner frequency. So something like this we may have if we have a 0 in the system. This curve is very good approximation, or very good, gives very good value for omega which is greater than omega z, and gives very good value as well when omega is very smaller than omega z. In between we meet it, these curves meet here at omega z for the approximate or asymptotic Bode plot. For the actual plot, there will be some difference. The actual plot will go something like this. It will meet the these two curves at little far from omega z. So at this point, at this omega z corner frequency, we have some error compared to the actual, and this is basically equal to minus 3 dB. For a first order system we are talking about. So this is enough to understand that for when we are dealing with the actual system, we should not consider only the asymptotic plot. Let's say when we are determining the values or gain at this point, it is not just the approximate value, but we need to consider this minus 3 dB deviation. So now from the asymptotic curve, we know where it is going to meet, and at any point we can say that yes, here we will have 3 dB of difference. So that's the only difference we will have from the actual magnitude plot. Now coming to the phase plot. So what we have here is that we need to take phase of this transfer function. So three components are there: constant, zero, and pole. So all three we have taken out. Now the constant will have zero phase always. So if you plot the Bode plot corresponding to the phase plot of the constant portion, it will always be zero, irrespective of what frequency you are talking about. The other two sections which are involving a zero and pole, so notice the sign. Whenever we have a zero, the phase is always positive. So it is always increasing with the frequency, and for the pole it is always reducing. But how the approximate curve or the asymptotic curve is going to be defined, that approximation we can see over here. When we talk about, let us say, any frequency which is much lesser than the corner frequency, this is basically the value is insignificant. So the value is very close to zero. Whenever we talk about very large frequency, then this value is very large, and we can say that yes, okay, approximately it is going to 90 degree. And in between, at this corner frequency, this will exactly match at 45 degree. So when we say very small, we mean that 10 times away from the corner frequency. So 0.1 times of the corner frequency or below that. And when we say very high, that is 10 times of the corner frequency. That is the general demarcation we have. Now, if we need to plot the phase of this system, so obviously this is, let's say, for a zero. So we will have 0 degree line over here. We are plotting with respect to omega, and this is say 45 degree, and then we have 90 degree here, and say this is the corner frequency omega z we are talking about. So we need to clearly mark these 2 points, 0.1 z and 10 omega z. So because this is semi-log graph or semi-log axis, so we have this distance same because the ratio is same. So this gap will be same. Now what will happen? The asymptotic plot for phase will start from this point. It will meet 45 degree at omega equal to omega z, and then it will match the 90 degree curve over here in this fashion. Okay, so this is how it will look like. The actual plot may slightly deviate, but definitely at this point it will match, and then it will go something like this. Slight deviation may be there, but it will be very, very close to the linear curve, what we have drawn. Let's say if I draw in red. So this linear graph gives us a lot of information about how our system is going to behave and what it is going to do. So if we are drawing for a pole, obviously it will go from 0 degree to minus 90 degree, meeting minus 45 degree at omega equal to omega p. And if both are coming together, the cumulative effect can be joined together, like how and where these poles and zeros are located. Let us say I take example of this transfer function. Now if I have to draw the magnitude and phase plot of this, so say that omega p is less than omega z, which means we have pole coming before the zero. So what will happen? We will have some positive case, so it will start from here, and say here we have omega p, then we have omega z, So what will happen that from this point up to this, the magnitude plot will fall at the rate of minus 20 dB per decade. And then at this point, the 0 will add plus 20 dB slope to this. So effectively, these two slopes will cancel out and this will continue with a flat curve. So the total gain plot will look like this. So these two slopes are cancelled. What is coming on account of the pole and what is coming on account of 0. Fine. Now, when we draw the phase plot of this system, see, ultimately, now if you guess from here, from the transfer function, if your omega is very, very less than omega p, what should be the phase of the system? What should be the phase?
So 0 degree.
0 degree. Okay. And if omega is very, very large than omega z, what should be the phase?
Minus 90.
Minus 90 degree.
Okay, think again.
0 degree.
Yes. Why 0?
Minus 90 and plus 90 will cancel out.
Yes, exactly. Whenever it goes very far from the pole, it is minus 90 degree. And whenever it goes very far from 0, it is plus 90 degree. Effectively, these two will cancel and again it will come back to 0. So you need to see the effect of this pole and 0 in terms of their location, where they are. For example, when I draw this here, say I am marking the point 1 and 10 times of this corner frequencies. So what will happen? Let's say this is 0 degree line. So we have say 45 degree here, we have 90 degree here, we have minus 45 degree here, and we have minus 90 degree here. Okay, now if I ask that how this curve will behave, the phase plot. So what will happen? It will start from 0, correct? And then because the pole is coming first, we have omega p first, so it will definitely go towards the negative. And because our 10 omega p is coming before 0.1 omega z, so it will definitely go and meet 90 degree. Minus 90 degree it will meet here and continue with that phase up to it meets 0.1 omega z. Now from here the phase will start getting lesser 0, like lesser negative. So it will start moving towards 0. Now some positive slope is there in the graph. So at 10 omega z, this 0 will add another 90 degree to this phase. So total it will come back to 0 degree. Do you understand this point?
Yes.
Yes, sir.
Yes,
If
sir.
these 2 points are overlapping, say this 0.1 omega z is coming before 10 omega p, so what you need to do, you draw both the curves separately. Let us say one situation I am considering over here. You have omega p, then omega z is somewhere close. So 0.1 omega p is here and 0.1 omega z is here. Sorry, 10 omega p is there and 0.1 omega z is here. So these are the curves. Let us say these are the points. Now what you do to get the phase plot? Obviously, because pole is there first, so it will definitely go towards the negative side. And omega p is certainly coming here before any other frequency, so it will meet minus 45 degree. There is no problem. Now the way to do is that you draw these curves separately. Say this is on account of pole And then you have on account of 0, say I draw with black line. So it will start from here and it will meet 45° here. And then it will continue with 90° here. So this joining here and here. The resultant will be actually sum of these two. Understand the point? So ultimately what will happen here after 10 omega z, 90° and minus 90° are going to cancel. There is no doubt in that. Here there is only pole before this 0.1 omega z. So it will continue in this manner. Correct? Now what will happen here? Because these two slopes are cancelling each other, so up to this point it will go flat. And then this has become constant. There is no further addition from this side, but this is growing. So it will slowly start reducing and it will come back here and then continue. You understand the point?
Yes, sir.
So basically these two curves we are adding, nothing else. The green curve and the black curve. So similarly for any other scenario, even if it is phase plot or gain plot, anything, you can simply draw all the lines separately. Let's say for every component, whichever pole or 0 or constant value is there, and then simply add it according to their magnitude and the way they are coming, the slope and everything. And you will get the resultant phase plot or resultant gain plot easily. Correct? This is important tool for getting the control design. That's why I am emphasizing a little bit more on this. Is that clear?
Excuse me.
Fine?
Yes. Yes, sir.
The slope of both graph will always remain the same.
Yeah, because both are same, right? First order. If it is second order, then instead of going up to 90°, it will go to 180°. Double slope.
I mean, sir, for the negative slope and the positive slope will be same. Right?
Yes, of course. We have same thing, right? Tan inverse omega by omega x. Nothing else is there.
I mean that omega, it will not depend on the omega value of omega z and omega p.
See, this is what I am saying. This is approximate. Approximate means we are matching these curves, the approximations what we have got for the phase. These approximations we are matching through lines.
Yes, sir.
So this is the point what we are meeting from 0° to 90° through 45° at omega equal to omega x we are meeting. That's why it's a line. Otherwise it's a smooth curve if you draw it actually.
Yes, sir.
So definitely it will change slope somewhere if you see the actual graph. But this line is very, very close to this. So it is enough to tell us the design parameter is good or bad. Fine?
Yes.
Okay. So still 4 people are keeping their camera off. Why? Are you not interested in the class? See, this we are going through very interesting point in our course. Okay. So you all have to participate here. Otherwise, if you miss, then it will be difficult to catch further. All of you are there, or some are just there in the meeting?
Yes, sir, I am there, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So keep your camera on so that I can understand whether you are getting this point or not. Your faces are visible, then I can guess that. Otherwise, it is difficult. No, it should not become monologue. Okay. Now, this tool we have got. Okay. So what next we have? Now we have to design the control system. So let us say, as of now, not going into too much details, I give the option that, okay, we use PI controller. For obvious reasons, it is fast enough and also the steady state error is 0. Correct? So this is what we tool as our, this is what we use as a controller for our system. So the transfer function for PI is basically this. Now this is what we are going to utilize. So first, let us design the current control structure. So next half an hour is going to be little intense. So wherever you miss the or lose the track, just remind me. Okay, so current control structure, what we have, some current reference given. We have the feedback IA, then this is given to the controller. And then we have the V reference generated, which is basically magnified by the converter. And then we have something else over here, which is the back EMF getting subtracted. And then this is plant, which is generating our IA. Fine, right? No problem in this.
Yes.
Now we have been saying that we are dealing with, let's say, linear controllers or linear systems. But just let me see if any point is missed out in the Bode plot section. Or I think I have covered all the points, whichever were important. Okay, yeah, one point I should mention before I move to design is that from the Bode plot, when do we say that we have a stable system? So basically, we have phase margin at the gain crossover frequency. This you understand, right? These terminologies you know. So at this gain crossover frequency, the phase margin should be more than 0 degree, which means the phase should be less than minus 180 degree. So phase margin, when I say this is phase, so basically this curve, when it is going negative, we have 180 degree line over here. So how much gap is there from 180 degree to this phase at which the gain crossover frequency is occurring? That is called as phase margin. So whenever we have positive phase margin, we say that the system is stable. There is no problem. Fine. So this is the only point which we need to remember as of now in the Bode plot section. And then we are ready to design our controller. Okay. Now what we have basically here, if you see closely, that there is something which is getting subtracted over here in the VA, whatever is generated by the converter. Now what is the effect of this EB? If you see the equation, what we have, IARA plus LDIA dt minus EB, sorry, plus EB. Correct? Or if you write it in the S domain, you have, so capital letter denotes basically the Laplace transform. So I will simply use that. Correct? Now, if you see this part, except this EB, the rest of the portion is kind of linear. By linear, what I mean that IA is something governed by this relationship. If you increase VA, this will increase. If you double VA, IA will double. But when EB is there, you cannot say that, right? So there is some nonlinearity in this equation, which is on account of EB. And EB is something which our system itself is generating because of the speed. This is back EMF, dependent on speed. So some arrangement we need to do to make this system linear. So for example, if you shift this portion on this side and name this as some new voltage, say VA star. So then VA star and IA are kind of in linear correlation. You understand the point? VA is not having linear relationship with IA, but VA star, which is another, say, intermediate voltage or whatever you want to call, this is something which is linear. So basically, whatever this extra term is coming in this VA star, what we do to linearize this, that we feed forward this. We compensate this system, this component in a feed forward way. So we just add this system or this value somewhere so that the effect of this EB subtraction is nullified. We add it somewhere in the controller output. So if I draw the block diagram, what happens with that? Let's say some X we have added, and then whatever this is generated here, V star, that is basically driving this system. Now the meaning is, let us say when X is not there, now who will compensate for this EB? Basically our controller need to generate so much voltage that EB is compensated, isn't it? You understand this point?
Yes, sir.
So this V star basically consists of one component which is coming from the controller, another X which is equivalent to EB, which means now whatever output, say Y, generated by the PI controller is not seeing this EB as any problem. This Y is not affected by EB. So that's what we have done. We have feeded this component in advance in the controller output so that the effect is nullified. So this is called feed forward compensation. Understood the point? So when X is there and when X is not there, the difference would be that controller will have to work for the EB. So in this case, the Y is not affected by EB. In this case, Y is affected by EB. If EB is more, Y has to compensate for that. So we are trying to make our controller as much as possible independent of any nonlinear thing. Fine. So with this understanding, now we have a simplification for this control loop as IA star, and now let me write this transfer function for the current controller. Say I will use KP I and KI to distinguish between the other PI controller. And now because this is compensated, so I can directly write the VG gain, and this is also gone. So we have the linear plant over here. Fine. No problem in this, right? Any problem in this?
No, sir.
Good. Now we have open loop system, open loop transfer function for the current loop given as correct. Let us rearrange this. So what we will have, this coming as the open loop system. Fine. Now what we have basically, that we want some good response or fast dynamic response from our system. So the component which is responsible for slowing down the system is basically a slow pole. So this is something which is coming there in the denominator. Now this will respond only at this time constant LA by RA. Now, if we can somehow compensate this slow pole, then our system will be independent of this variation, the time constant LA by RA. So simply if we use this 0 to compensate for this pole, which means KPI by KII, keeping simply equal to LA by RA. So this gives first equation or first relationship for designing our controller parameters KPI and KII. So this is first relationship. Now, if we are maintaining that, what we have basically, it is reduced to this. This is the open loop transfer function now, effectively. And if we take unity feedback and write the closed loop control or closed loop transfer function of this, what it will become? Fine. So this is nothing but GOIS by 1 plus GOIS. Correct? Is this fine for you?
Sir,
Now, yes.
sir, that VG is converter gain. Sir, why we are writing that gain as VG? Means.
That is what the model is, right?
Okay, sir.
That's what we have. So what it should be?
Input DC voltage.
Yes, that is what we have modeled as our converter as, no?
Okay, sir.
So whatever system is there in our control loop, everything we are modeling. We have controller, we have power converter, we have the motor. Motor electrical system only, because we are only designing the current control as of now.
Okay, sir. Yes, sir.
Fine?
Yes, sir.
Now, effectively, if you see, yes.
Sir, can you please repeat the point slow pole where you mentioned slow pole?
What to repeat?
Sir, what is slow? Why you are writing it a slow pole?
So LA by RA, generally I have told, right, it is like few tenths of millisecond. So it could be 10 millisecond, 20 millisecond, something like that. Okay, that means any step response or any input if you give to the system, it will take, let us say, some 100 millisecond, 5 times of the time constant to reach that value. This is of the order of 0.1 second. So generally in terms of control design, when we are saying, these are all called very slow response, sluggish response. You are giving at t equal to 0, but you are seeing the output only at 0.1 second. So which is what we are trying to compensate over here. This is called the slow pole, which is not responding so fast, and it is not under our control. We can't do anything about it. It is what system is having. We cannot change LA, we cannot change RA once the machine is given. So we are trying to get rid of something which is not under our control.
Okay, sir.
So ultimately what we have is basically this transfer function. Now, if you see the Bode plot of this, because this is first order system, so phase is going to remain at minus 90 degree. So no problem. It is still having phase margin of 180 degree at least, sorry, 90 degree at least. There is no problem at all in that, right? So what will happen? Based on the gain plot, we can design the other parameters, the other relationship we can get, what should be there for KII. So let us say this is the corner frequency, something like omega x if I say. Okay, this corner frequency corresponds to this S by omega x. So omega x is nothing but KII VG by RA. Fine. This is fine, right?
Yes.
So we are simply plotting the gain plot for this. So what will happen initially, the value will be 0. And then at omega x, it will start going at minus 20 dB per decade. The actual plot will be basically, it will deviate by minus 3 dB at this point. This minus 3 dB deviation, what we have seen earlier, also defines what is called as the bandwidth of the system. So when the system gain falls by minus 3 dB at a particular frequency, that is what is defined as bandwidth of the system. Correct? So in a way, our omega x is nothing but the bandwidth of our system. You understand the point? These are all standard definitions, what I am only stating. Yes or no?
Yes, sir.
Yes, sir.
Now the question is, what should be the value of this omega b omega? What should be the value of bandwidth? How do you design? The question comes to that. So first we need to know what is the impact of bandwidth on the system. What is meaning of bandwidth? So more physical, see, when we see the frequency plot or no, in the frequency domain, we cannot judge the system very well from the physical response point of view. But when you have something called as step response or time response of the system, then you are able to see it more clearly. Let's say we give step input of 1, let us say. So we may have several response. Let's say one response could be like this. Another response could be like this. All these are first order. So that's why no overshoot, no this thing will be there. Settling a double second order kind of thing. Let's say 3 curves I have drawn. Say this curve corresponds to bandwidth 1. This curve corresponds to bandwidth 2. And this curve corresponds to bandwidth 3. So the relation between these three bandwidths is bandwidth 3 is basically higher than bandwidth 2 is basically greater than bandwidth 1. So if I talk about the time constant of the system, so what I assume that the system is settling within 5 time constants. For t equal to 5 tau, it has settled. So now time constant is something inversely proportional or basically inverse of the bandwidth, omega b omega. So which means if we want to design our system for a very fast response, we need to have very high bandwidth. So if bandwidth is increasing, your response time will reduce. Now you got the idea how bandwidth should be.
Yes, sir.
Yes, sir.
Clear, right? Now the quality we know that okay, we have to choose the bandwidth which should be as high as possible. This is what we understand. That is our general understanding also about any system. Bandwidth should be as high as possible. But then can we say that bandwidth can be infinity? Or is there any practical limitation of that? Is there any practical limitation on the bandwidth?
Yes, sir. Sir,
Yes, sir.
if we increases more bandwidth and more disturbance.
That's
Yes.
okay. Disturbance and all we have seen, right? The closed loop control is able to solve everything.
More harmonics will be there, sir.
Which harmonics? I have not talked about any harmonics so far.
It might be limited by the power electronics.
Yes, to an
Switching.
extent, correct. So definitely anything what we are generating is coming on account of some power converter. We have the VG gain, but it is actually not just a variable register or something which is generating the output.
वो लास्ट वाला होगा सबसे इधर वाला हाँ वो
Deepak, can you mute yourself? So basically what we have, this is generated, the output is generated on account of some PWM operation, right? So basically this Vref is fed to some carrier waveform, and then the comparison generates this output voltage, say Vg, and 0 it will be going, and the average value will be coming out. So we are somewhere bound with the switching frequency and the operation of the converter. Understanding my point? So the practical limitation, because these concepts will take some time unless you do it yourself and think little bit more. If I tell everything, it wouldn't make any sense. But say if I tell like a thumb rule that the bandwidth you can take simply as 1/10 of the switching frequency. Say we will discuss why during later sections of this course. First, you absorb some of these concepts what I have discussed over here. So bandwidth should be 1/10 of the switching frequency. This you take as thumb rule as of now. And with this you design. So obviously bandwidth cannot be infinity. It is restricted by this. So then our design comes down to this value. So we have KII into Vg by Ra going equal to omega b omega, which is nothing but 2 pi fsw by 10. So this is the second relationship what we have got, and two variables KPI and KII can be solved. Fine? Yes or no?
Yes, sir.
Yes, sir.
Good. Now once we have got this KPI and KII values, what we have basically that current control is simply coming as a first order system. The whole current control is basically reduced to something like a first order transfer function, which you can say is having this kind of structure. And tau I is nothing but 1 by omega b omega. Say I distinguish by putting an I over there. Fine? Up to this point you are clear?
Yes, sir.
Yes, sir.
Yes, sir.
Now this block we will use for our speed controller design. Of course, we have only designed inner control loop for our system. Now we go for outer control loop, which is actually little more involved, and we will see why. Okay, another 10 minutes. Let us be very, very attentive and listen to this. So what we have basically, we have omega reference, omega feedback, then we have the controller. Say I say that it is PI controller again, so KP omega plus KI omega by S. The structure is there which is generating IA reference, and our current control loop we have seen that it is reduced to S tau I, which is generating IA. So EB, everything whatever is coming within this, that is all taken care, nothing to worry. Then we have C, and the load torque is compensated over here. And then we have the first order system over here, giving the feedback omega. Now the difference when we are measuring current and when we are measuring speed, the difference could be that generally the speed encoders and speed sensors are more noisy compared to the current controller, current sensor. So we need to put a filter over here to remove all the unnecessary noises. And filter may have a cutoff frequency of something like 10 Hertz. Correct? So then I can say that my filter is having this kind of transfer function, where tau f is nothing but 1 by 2 pi 10. This is what is extra element which is getting inserted for practical reasons. Another thing is this tau L may be there, may not be there, is not defined by system. It is something, it may be there, may not be there as a disturbance. So we can simply ignore. Whatever compensation has to be done for this, we cannot do in advance because it is not there always. It may be there, may not be there. So whatever response change this will have, that will be compensated purely by this controller. There is no running away from that. We cannot avoid this. So whatever disturbance this will create, our controller will take care of that. So here we are not doing any feed forward compensation for this. Simply we are ignoring the disturbance. Now, the remaining portion, whatever we have, if I write the open loop transfer function for the speed, we will have Kp omega plus Ki omega by S. Then we have 1 by 1 plus S tau I, then C by B plus Sj. And then the filter, what is coming over there, 1 by 1 plus S tau F. So in total, if you see, it's a big transfer function what we have now, something like fourth order, isn't it? Compared to what current was having first order, that was very, very simple. Now here we have much bigger transfer function. So the design definitely has to be little more involved. Now one thing we need to notice that when we are writing this frictional coefficient involved with the mechanical time constant, this also is many a times very, very small. So let us take the worst case scenario and simply take B equal to 0. We do not consider this at all. At the best, it can be there, which will improve the performance. But if it is not there, it wouldn't harm anything, because we are anyway considering this as 0. Fine. So the remaining transfer function will become, and I rearrange this also, Ki omega by S, C by S j, S tau I, and 1 by 1 plus S tau F. Okay, the controller part is left, 1 plus Kp omega by Ki omega S. This is fine, right? Is this fine?
Yes, sir.
Yes, sir.
Now notice that the difference from the current control loop, we have two poles at the origin. So if you draw the Bode plot of this, now the phase plot will be coming into picture because we have minus 180 degree phase in the beginning itself. Sorry, let me draw it properly. Say this is our magnitude 0 dB line and this is our phase 0 degree line. So what will happen, because we have double pole coming at the origin, so definitely this will have a slope of minus 40 dB per decade. And the phase plot will be at minus 180 degree, sorry, it should be here, say. So the phase will be here. Now, from the phase, you can say that this system is inherently unstable. We cannot do anything about it because phase is already minus 180 degree. So even if you try to cancel the pole 0 using this controller 0 and any other pole, this is certainly not going to help. You will not make any difference in the phase plot or the gain plot or magnitude plot of this. First, let us do another approximation that we have two poles over here. Let us merge and make one common term out of it. So then it will simplify further. We have 1 by S tau F and 1 by S tau I. So we have seen that the F is something like 10 Hertz. So response time may be something like, let's say, tau F may be something of the order of 0.1 or less than that, 0.1 you can say, something like that. Okay. And this also, or let us say 0.1 for simplicity. The order of the time constant could be something like that. The tau I can have time constant of the order of something like 0.01 second. So now, if you combine these terms together, we have s tau I plus tau f plus s square into tau I into tau f. So what is happening over here? The product term of tau I into tau f, this will be something of the order of 001, which is 1 millisecond. Correct? Very, very small compared to the other term what is coming over there. So we can approximate and we can ignore this product term and we can write this as 1 plus s tau 1. Let's say tau 1 is basically nothing but tau I plus tau f. So this is one approximation what we can have over here. So these two poles are effectively combined to a common pole. Fine, because everything what we are talking about here is far from the corner frequency which is at the origin. So now I will write the term over here. So this simplifies little bit. Like this. Okay. Now what we have, even if we cancel this pole and 0, that is not going to make any difference in the phase or gain plot in the beginning. And if the system is unstable, nothing can be done. So we need to do something different other than pole 0 cancellation. So this is where we get into what is called as the symmetric optimum method. Okay, let me write here itself. Symmetric optimum method says that you do not cancel the pole and 0, but you place this pole and 0 such that the phase improves little bit and then goes to wherever it has to go. So basically at the gain crossover frequency, the phase margin should be positive. As of now, it is 0. So our only aim is to locate this 0 and pole such that the gain crossover frequency becomes the gain crossover frequency, the phase margin becomes positive. Correct? So let me write this as, for just simplification, I write in terms of pole and 0. Let's say our 0 is something like omega z and the pole is something like omega p. Now what I do, I place the 0 before the pole. Say 0 is coming over here. I have placed it somewhere and my pole is coming somewhere here. Correct? This is what we have as pole and 0. We can do, because omega z is because of our controller. So we can place position kpw, kiw and all that. And this is anyway there. And filter of course is also there. So we can position omega z such that it is coming before the pole. Now what will happen to the plot? How it will change? The gain plot, which is having minus 40 dB decay, let us reduce the slope little bit so that it doesn't go to 0 so quickly. Yeah, minus 40 dB per decade will improve to minus 20 dB per decade. Okay, or just redrawing it for clarity. Minus 40 dB becomes minus 20 dB and then again continues with minus 40 dB after. So in between what has happened, this has gone to minus 20 dB per decade. And wherever this is crossing, that is basically our gain crossover frequency. Fine, right? There is no problem in this. Clear?
No, sir. Clear, sir.
Yes, sir.
Okay. Now, what will happen to the phase, because we have 0 coming before the pole, so this will start improving. And somewhere here, let's say if I draw linearly, it will go to some maximum value and then it will start reducing and go back to minus 180 dB. So at this point, we will have some positive phase margin. You understand the point?
Yes.
Yes, sir.
Correct?
Yes, sir.
Now, this is basically the point where it is crossing with minus 40 dB per decade, or the gain crossover frequency for the open loop system is basically our bandwidth. That's what we have seen in the closed loop control also, in the current control also. So at the gain crossover frequency is basically our bandwidth. So at this, we are getting this much phase margin, and symmetric optimum method says that if you position these three frequencies, omega b omega, omega z and omega p, equal distant, then the phase margin is best. So what I'm trying to say is that omega b omega is some a times of omega z, and omega p is some a times of omega b omega. Okay, so already it is past 11. I need to stop. So what you do basically, I give you the expression to derive the kpw and kiw values. So actual graph may be little more smooth instead of line, but the nature will remain very much close. So what you have to basically now come up with the expression that phase, let us say we decide a phase margin of PM. So the phase should be something like this for the whole system at omega b omega. And the gain, because it has to be gain crossover frequency, so it must be 1. So using these two conditions, can you, and given phase margin, say 45 degree. So can you derive the expressions for kpw and kiw? Okay, this I give you as an exercise. So let us see. So tomorrow, do you want class? It has already been 4 classes in this week. So I am little thinking, no,